Hi, my name's Amelia. I am doing a KTP project with Photech, which is situated in Hastings, East Sussex, and the University of Leicester. My KTP project is investigating machine learning solutions for high-speed data analysis and imaging for a single photon timing detector. So Photech currently have a detector which is capable of time-stamping single photons to 60 picoseconds, and a planned development within the company is to increase the spatial resolution to megapixel scale while preserving that time resolution. And this would create an entirely new class of photon detection system, which would enable novel scientific methodologies in many scientific fields, such as observing fluorescent decay in biology, and also observing qubits for the implementation of quantum computers. However, due to the event rate that the timing electronics and the detector can handle, traditional algorithms are starting to restrict the processing of the data coming out of the detectors, especially because the huge volumes of data coming out of these detectors can be in the region of 10 gigabits per second per detector. And for example, in particle physics applications, you're going to have many detectors. So the question we're trying to solve within this KTP is, can we use machine learning solutions to determine the photon event coordinates with the objective of being able to process one single photon in around 10 microseconds, which gives us kind of close to real-time processing speed. But if we really wanted to move to real-time, we'd need to be able to process each single photon in around picoseconds. So within my project, I've only been working with a simulation of the detector at the moment, not real detector data, because the calibrations and the noise within the real detector is something we want to work up to from a simplistic case to make sure the neural network performance doesn't decrease so much with all these calibrations implemented. So I have worked with a simplistic case where the neural network, so actually a convolutional neural network, receives inputs of packets of data for each charge distribution. So if you look at this picture here, just to clarify, the neural network isn't actually fed a picture, it's just fed packet information. So it will be fed the signal amplitude for each channel ID and the time that event occurs on the channel ID. And from that, it needs to give the output of the x and y coordinate of the electron. So I've fed the neural network a simple case where there's only one event happening on the anode, so each event is separated in time by quite a lot, and the neural network doesn't have to worry about multiple events happening at once. So that neural network was actually quite successful and would output the x and y coordinates of the electron on the anode to an error of 0.3 pixels. I'm still working to actually improve that a little bit. Also, my current work is now focused on making the simulation of the detector more realistic. So I'm currently trying to allow the neural network to handle having coincident events. So for example, if you looked at this image here, that would be an example of two events happening on the anode within around 2 to 2.5 sigmas. So a sigma is around 60 picoseconds here, the resolution of time stamping a single photon. So these events can happen within 120 picoseconds of each other. So to combat that, at the moment I'm trying to use a neural network to control a state machine which effectively bins the packets of information coming in to binning them into the correct charge distribution, and then they are fed into the neural network, which resolves the x and y position of the electron that's hitting the anode. Furthering this, there's quite a few more complications within making the simulation realistic. So the simulator also has to be able to handle the noise and calibrations which are seen within the detector and the electronics, because we need to be able to assess the neural network's performance given a more realistic situation, so that can be a threshold for what the performance will be like when we test it on real detector data. So for example, the noise effects that need to be included within the simulation are listed here. So if I give you one, for example, the laser size hitting the window of the detector, gives an error in the position of the electron of around 0.2 microns. So we need to evaluate how well this neural network can handle all these noise effects, and see that as a threshold for the performance. So once all these effects are taken into consideration, hopefully we'll have a machine learning solution that can take the outputs of the electronics from the detector and process to around microseconds each event for the x and y coordinates of the electron. And then hopefully future work would be to assess how well this works on real detector data as well.